We are now ready to take a look at the multivariate Taylor series. And as I mentioned in the previous video, there's some notation that we need to really weed through to make sense of it. But once we get it, it's pretty straightforward. So suppose we have a function that inputs a vector. Okay, so this is, if I'm reading this in the English language, I would say a vector that has A components in it. All right, so it has A inputs, so it'll have like x1, x2, x3, all the way up to xa. So if A is 100, it would have 100 inputs. And outputs a function value, which is just a real number, right? So it's only going to have one output. Notice this is the same thing as R1. So one output. And this says that there will be A inputs. So we represent that input as a vector. And we wish to approximate this function output at some point x naught. So x naught you can think of as having x1, x2, however many variables there are, which we know there are A input variables, xa, right? So I'll write this as x1 naught, x2 naught, all the way up to xa naught. Maybe I should put a comma in there so as not to imply x10, x20. All right, and so that's going to be my initial value vector. Now we're going to define this delta vector to be the difference between our input vector, our variables. These are just our variables, and these are our, this is our point of interest. So if you imagine what this looks like, then what we should see is that it would have, something like, let's just say it's x, y, z. We have three inputs, x, y, z, subtracting away the initial condition. Now, if we recall from the original Taylor series for a univariate function, this is really just shifting our polynomial over so it's centered at x naught, y naught, z naught. Okay, so that's just a vector of all of the shifts. And then the capital D, this is the eighth total derivative tensor of f with respect to x. And at that point, substituting in our initial condition. So it's basically taking the derivative, right, of the kth derivative with respect to the vector x. And all we mean by total derivative is that it has all the derivatives. That's all we mean by that. It just has all the partials with respect to x, right? So it'll just have all those partials. We call that the total derivative. And it'll be because as we get more and more of these, we're going to have to add more and more dimensions. So we'll see that pretty soon. Then the multivariate Taylor series says that you can get an exact fit, right? Notice there's an equal sign here. This would be an exact fit, but only if you used infinitely many terms in that expansion. Now, just like the Taylor series, it does the same kind of thing. It's just in the multivariate realm. If you reduce this down to just one input and one output, you'd see that it's really just the Taylor series approximation. Notice that it's still dividing by the k factorial, and it's the derivative times the shifts, right? So if we remember from the Taylor series polynomial, we'd have a derivative evaluated at our condition multiplied by x minus x naught. And it would be to the first power, to the second power, etc. Okay, well, what does it mean? Okay, this is not, the k here does not imply an exponent, it's a derivative. So I think in regular univariate, we'd put parentheses around it, but for whatever reason, we don't use that notation here. If it makes it a little bit easier, you put the parentheses up there to emphasize that it's not an exponent, it is a derivative. And down here, I mentioned that as well. Okay, delta to the k power, well, if delta is a vector, how do you take a vector to the kth power? Well, we're kind of lying with this notation just a little bit. I'll just say kind of an exponent, not in the strict sense though. We're not just exponentiating each of the values inside of this here vector. We'll show that in a minute. Now we want to approximate, right? We can't have infinitely many terms. So what we're going to do is we are going to approximate, and now notice that this is an approximate fit. Because, again, simply we can't have infinitely many terms. And we're going to stop at n terms. And with n terms, that will be an nth, well, I'm sorry, we have that written up here. That will be an nth order Taylor series approximation. So the bigger n is, the more terms we'll have, the better the fit we'll get. Here are a few important notes. As mentioned, the k in the derivative tensor is not an exponent. It is the derivative order. So like k being 5 would be the fifth derivative tensor. The first derivative, by the way, is just the gradient of f with respect to x because, well, that's what the first derivative is. The first derivative with respect to x is exactly just the gradient, which we might write as grad f. Well, the second derivative, if you're taking the derivative of the gradient, then you're getting the Hessian of f, and the Hessian, remember, just contains all of the second order and mixed partial derivatives, and it tends to look something like this. You'd have fxx, fyy, and then here you would have fxy and fyx, and all that means is that we're going to have all of those derivatives. So notice that we go from if you have only two variables x and y, that's kind of what I'm implying here, is just for simplicity, two variables x and y, then this will just have fx and fy in it along the rows. And the third derivative is the derivative of the Hessian with respect to x. Well, how do you do that? Well, in order to do that, to take the derivative of all of these derivatives with respect to x and with respect to y, if you only had two derivatives, you'd have one matrix which would have like fxxx, I'm probably mixing these up, but that's okay, fxxy, fxyx, fxyy, and then you'd have to do the same thing, but with the, I probably should have put that x on the end, but that's okay, we'll just use the first derivative. Fy, xx, fy, xy, fy, yx, and fy, yy, right? So notice that now we have a tensor. We have a 2 by 2 by 2 tensor, because each time we take a derivative, we have to add another dimension corresponding to the number of variables we have. Again, I think I mixed these up. I probably should have, not changed the first element, but the last element, but it shouldn't change anything. So just to illustrate that. Now, the k in the delta to the k is a bit like an exponent, but not in the way we are used to it. It actually represents an a by a by a, well, depending on what value of k this is, you'll have an a to the k tensor. So, right, it just every time you multiply a vector, and this is actually called what we call an outer product. When we take, say, an a by 1 and we multiply it by a 1 by a, then we're going to get an a by a matrix. But if we take that and we sort of repeat that process, each next value of a, 1 through a, will generate, it's getting kind of messy, a separate matrix, right? So this will be an a by a, this will be an a by a, and how many of those a by a's will we have? Well, we'll have a of those a by a's, and hence we get a by a by a. Now, the good news is we're not going to represent this as tensors. We're going to reshape the tensors, as we've learned, that is fairly common. We're going to reshape them into vectors. So that's the good news. Now, just to point out what these look like, if you had delta, the delta vector, that would just contain, remember, a variables. So I've just labeled them x1, x2, all the way up to xa. And then we're, subtracting away those initial values. Now I'm kind of using some messy notation here, but this is just to emphasize that, I may run out of alphabetic letters because these vectors could contain more entries than the number of letters in the alphabet. So I am just denoting x1 comma 0 as the point. These are actually the point values, the x0. And okay, so what would you do if you squared that? Well, we've already mentioned that by definition, what that would do is it would produce the sort of the two-dimensional tensor. And then if you did that again, you'd get the three-dimensional tensor. But it makes a little bit more sense to write it like this. Delta, the ith component. So in the delta squared matrix, the 2 by 2, it would actually contain the product of delta I times delta j. Okay, so what am I saying here? Well, let's say that just with two variables, we had x minus x naught and y minus y naught. So that's, let's just say, our delta vector right there. So you can see that delta 1 would be this guy right here. So we're going to label that delta 1. So that's just an index saying in the delta matrix, the first component. Now, because it's a one column, we only need one index. We don't need to say which column and which row, because there's only one column, so that index will simply represent the row number. So if you were to produce the delta squared, I apologize, this is getting a little bit messy here. I'm going to erase some of this stuff here. What this would look like is if you took delta squared, well, by the definition, we're saying that I comma j entry. Okay, I represents to the row number, j corresponds to the column number. So because, remember, we said that this is going to be a by a, in our case, this is a by 1, a 2 by 1. So an a by a would be a 2 by 2. Now, if we want to know what is the 1 comma 1 entry, that will be this guy. This will be delta squared 1 comma 1. That'll be the first row, first column. That will be from the original delta vector. It'll be the first component times the first component. So what's the first component? Well, it's x minus x naught. So this will be x minus x naught times x minus x naught, which is just x minus x naught squared. In the delta first row, second column entry, which would be this one, by the definition, it will be delta I times delta j. So I is 1, j is 2. So it'll be x minus x naught times y minus y naught. Now, here we're going to get into the second row, first column, and that will be delta, by definition, here I is 2, j is 1, so it'll be delta 2 times delta 1. So it's really the same as this element here, it's just multiplied in opposite order, and that doesn't make a mathematical difference, right? Because multiplication commutes, it's commutative. And then finally here in the delta cubed position, delta squared, not cubed position, 2 comma 2, it'll be the second element of the delta vector multiplied by itself, which will just be that squared. Now, if you go into the third order delta vector, well, now it's going to have an I, a j, and a k. So not only will it have this 2 by 2, but it will be 2 by 2 by 2. So it just means you'd have a second one of these, a second matrix, and the first matrix, all of these elements would get multiplied by delta 1, right? So like you'd have x minus x naught cubed, x minus x naught, y minus y naught times x minus x naught. All of these would get multiplied by x minus x naught. And in the second layer, all of these same delta squared components would get multiplied by y minus y naught. And so you see every time we add, or I shouldn't say add, we multiply by another copy of the delta vector, we add another dimension in our tensor. Now we can call this 2 by 2 a tensor as well. but we officially get into tensor world. We have to use that label whenever we get into more than a two-dimensional matrix. Now it is so now that we have that paved, what we will do is remember that what we can do is we can take a tensor and we can stack it into columns by taking the, if it's a three-dimensional tensor, we take this second stack and we place it right below. And then we start to stack the rows as columns and we end up with a reshaped tensor. So we will end up doing that. We'll do that in our first example. Okay, I think this is a great place to stop this video and progress on to an example.